2 parts down, 1 to go. Welcome to the final piece of my technical deep dive series on the Micro Swiss all-metal hot end and nozzles. In the first part of this video series, I covered why you'd want to switch to an all-metal hot end, as well as the installation of that hot end on a Creality printer. In the second part of the video series, I actually demonstrated what the prints can look like using some of the more exotic filaments, such as nylon, polycarbonate, and acrylic. Now, in the final part of this series, we're going to be taking a look at nozzles. We're going to be taking a look at the metal these nozzles are made out of. We're going to be taking a look at the coatings of these nozzles and how these coatings are applied and why any of this makes a difference. So all of this was spurred on thanks to Micro Swiss providing one of their M2 high-speed steel nozzles that has a WS2 coating. So if you're interested in the constructions of nozzles, why you should choose one over another, stay tuned. This is going to get technical right here on Kersey Fabrications. Let's go. So that's it for the high temp filaments. I'd like to go give you my final verdict on all of this. But first, part 2 of this video, I'm going to talk a bit about these nozzles because, like I said, I was at IRF and I got to talk to the guys, and they did hook me up with a new version of their nozzle. This is the M2 high-speed steel nozzle. Keep in mind, this one is actually going to be a slightly different version of the nozzle. This is what's called a RepRap nozzle. It's not the MK8 nozzle that we're used to, but should have no problem printing with it. It's just a different shape, really. Same M6 threads. So what I'm going to do now, I'm going to switch over to the laptop where I've been showing you the tabs in my browser, and we're going to get a little geeky with these nozzles, because that's what happened. I sort of fell down that rabbit hole of wondering, what are they made of? What are the materials like? Kind of what their properties are? What am I getting when I switch from a brass nozzle, the different coatings available on it, and what am I going to get when I finally get to their highest end version, which is this M2 high-speed steel. Let's switch over to the laptop again and take a look at what I have up there. All right, so we're going to start out on the Micro Swiss website, where they have a page dedicated to their nozzles. They have their 3 nozzles they're offering here. They have a brass-plated nozzle, the A2 hardened tool steel nozzle, and the new M2 high-speed steel-plated nozzle. So the brass-plated nozzle starts life as what you would be used to as a brass nozzle. The brass nozzle has a thermal conductivity of 115 watts per meter Kelvin. I wouldn't get too much into like what exactly that means. We are going to take a look at that as a relative number. So again, 115 watts per meter Kelvin. And what they do is they take that brass, which is very thermally conductive material, and then they're going to coat that in what they call twin-clad XT wear-resistant plating with a non-stick compositive additive. So that plating hardness right here is going to be adding the hardness to the nozzle, because brass wears relatively easily when compared to nickel or steel that we have in these other nozzles. So we add this, it's going to give it a little bit extra life as we wear out that nozzle with more abrasive filaments. And this coefficient of friction right here, that tells us a relative value to the level of friction that the coating is going to provide when pushing filament through it. So I want to show you some tabs I found here on these different kinds of metals and the coefficient of friction that we have for each one. So brass. So first of all, I'm starting out with a 360 brass, which is what these are made of. And we have a chemical composition, primarily copper with lead and zinc. And again, the thermal conductivity was right down here. At 20 degrees Celsius, it's 115 watts per meter Kelvin. And then over here, I have the actual coating, which is this twin-clad XT. So twin-clad XT is a special composite coating, and I am going to need to take a step back here, trying not to be overly complicated, but in order to talk about a composite Electroless nickel coating, let's first talk about what it means to be Electroless nickel. So right here, what is an electroless nickel plating? So a lot of people have heard of the electrolytic nickel plating, and what that means is we apply a current to a bath of chemicals that has our metal in it, and that current then causes the nickel to adhere to the surface of the metal that we actually want to coat. Now, keep in mind, guys, I'm oversimplifying this a little bit. I'm not getting into all the chemical details because I don't want to burden it too much. But this is the basic functionality. Now, electroless nickel plating does the same thing, but without electricity. And I found this great article, which is on Advanced Plating Technologies website. Here again, you can see the web address if you want to take a look at it. And it shows really what's important is why is this different, or in this case, why is it better than the electrolytic nickel plating? And so the electroless nickel plating, as you can see here, does two things. Number one, the coating is much more uniform. As you can see here, we can see this constant layer of atoms, really, because it's really that thin, that goes around this base metal that they're adhering it to, compared to the electrolytic. What they're showing here, number one, it's a lot thinner. We see it getting even thinner as it gets up into this area. And down here, which is the base of this gear, this is this area here, which is covered up here. What we're seeing is that it doesn't even, that nickel coating doesn't even get into that part of the gear due to the actual process. But when we use electroless, which is basically, it's again a chemical bath that we don't have to use the electricity to, and the chemicals themselves apply or deposit that nickel onto the base metal. So what do we have here with the Twin City plating, this Twin Clad XT? Well, what they've done is, instead of only applying nickel, they've actually added additional chemicals, additional elements into the nickel bath, which are then applied to that coating, which gives us more properties, gives us better properties than nickel alone. As you can see, better coefficient of friction, better hardness than we get if we were just nickel plating. And so if we go back to the MicroSwiss website here, what we see is that here this plating hardness is 65 to 67, and that is also giving us this lower coefficient of friction. All right, so I would zoom through that. So now let's zoom over to using steel. So the other two nozzles are actually both steel. One's an A2 hardened tool steel, and one is an M2 high-speed steel. So before we talk about the coatings of each of these nozzles, let's take a step over and take a look at what those mean. So the A2 tool steel, for both of these materials, I'm on the Hudson Tool Steel Corporation website. Don't know if this is obviously where they get their steel from. This is just a great website where I found real solid statistics and information on these metals. So check out Hudson's Tool Steel if you want more information. Basically, what I wanted to look at here, what is it used for? So A2 tool steel is a versatile, air-hardened tool steel. It's characterized by good toughness, excellent dimensional stability, and heat treatment. A2 is intermediate in wear resistance between O1 oil hardened and D2 high carbon. Basically, it's a strong, hard tool steel, so they're going to use it in a lot of your hand tools, hammers, stuff like that. It has more information here if you want it. The thermal conductivity of the tool steel, I don't think I found this on this page, I found it somewhere else, is 26 watts per meter Kelvin. Again, compared that to the brass, it's obviously a lot lower. This may mean that you have to heat up your hot end more to make sure that you have enough of the heat staying in that piece of metal as opposed to brass. Not a big deal. I think on some of mine, I will run it 5 to 10 degrees hotter than I normally would for a brass nozzle. Not a big deal. What we do is, since this tool steel isn't necessarily the best friction, we get a lot better friction if we put that coating on it. So that's what they've done for theirs. Their A2 hardened tool steel has, again, that same twin clad coating. It takes a 62 HRC, which is just a hardness rating. Puts that 65 to 67, makes it harder. It makes the coefficient of friction lower. Basically gives it a lot longer lifetime than the brass plated nozzle alone. All right, Moving on to the M2 high-speed steel plated, which is the one I have here today. Let's talk about the base material again, that M2 high-speed steel. It is a tungsten base steel. As you can see here, we've got W right here is this tungsten here. Got a high tungsten composition, suitable for a wide variety of applications, well-balanced composite material. And again, this is a high-speed steel. What that means is that it really has really good applications in drill bits, tapping, milling. What that means to me is that it's going to do really well at high temperatures, because obviously that's what we're talking about when we're talking about steels that are going to be used in a drilling or a tapping. It's going to get hot. So this is also, I noticed it has a better thermal expansion, so I think we're going to maintain our size and our distance from the bed a little bit better. I don't know how much we need to worry about that, but it was just one thing I noticed here. And one thing, again, not on this page, it has a better thermal conductivity, actually, than that A2 hardened steel, with a thermal conductivity of 41.5 watts per meter Kelvin. Looking at our page here, so that gives us a harder base material, a base material that has better thermal conductivity. And what they've done with this one is taken the plating and the coating a step further. They now have simply an Electroless nickel plating applied to the outside. My guess is that is for both a little bit of better friction as well as some better thermal conductivity. And as you can see here, that plating is even harder than the plating here, so it gives us extra hardness. And then it has a WS2 coating, because that's going to take our coefficient of friction to less than half of the coefficient of friction that we found on the Twinclad XT. WS2 is exactly what it says it is, which I really kind of enjoyed seeing. WS2 means we have a tungsten disulfide. So we not only have a high tungsten, as we showed back here, a high tungsten in our high-speed steel. We have also added a lot of tungsten to our coating here. Thickness on here, I think it said here, it's a 0.5 micron. But that's all we need, because this stuff is very tough. And on top of that, it is has a super coefficient of friction on it, which means less scraping, less abrasion to the nozzle, because more of our filament is just going to slide right through without stopping off and damaging the nozzle more. If you want to read more about this, I found this on the Microsurface Corporation website. Again, this is tungsten disulfide, low friction, dry lubricated coating that improves performance and service life better than other dry lubricants by reducing friction and noise. It is also used as a mold release agent. So to tell you how low the friction is on here, think about other things that are used for mold release. This one obviously specifically for metal molds. So really, really good coefficient of friction. I think that they really did a good job here, kind of incrementally getting better on their nozzles. The brass plated nozzle, this is the one that we've been using the whole time up until this point. I've shown you the prints. It works really, really well. You know, out of the gate, there's no real reason to upgrade from that brass plated nozzle. But I do think, you know, depending on how abrasive the filament that you are actually going to be running through it, you might want to upgrade to the higher end nozzle. Let's go and take a look real quick at each of the pages. Here's what I was showing on the nozzles. An MK8 nozzle, this is what it looks like. It's what you're going to be used to on Creality printers. Here's the slightly different shape of that RepRap nozzle. Notice there's no difference in cost between these. This is their brass nozzles. Their brass nozzles are both $14.99 off of their website. The A2 hardened steel bumps up just about $5 or so. Takes us to $19.75. And these are available. Let's look at sizes real quick. Sizes on these MK8s are 0.2, 0.3, 0.4, 0.6, and 0.8. They have a few more options if you buy the RepRap nozzles. There are a few more options in the orifice size available on those. As you move up to these higher end ones, they don't have quite as many options available. But I don't think, you know, maybe I'm projecting a little bit, but I think these are probably going to be the most common sizes. You're probably going to go up from 0.4 if you're printing something abrasive, because it's going to have a lot of additives in it most likely. And With those additives, you are going to need a bigger nozzle, not a smaller one. So 0.4, 0.6, 0.8. Again, extra $5. As we move up to their new nozzles, again, these are the RepRap ones because that's all that was available at the time of this video. We go up about $5 more. So we got $24.99. I hate to make claims like this will be the last nozzle you'll ever need to own, but obviously from what we've seen, from the materials they're using, I think it's safe to say it's going to take a lot to wear out this nozzle. It's going to take a lot to wear out the A2 nozzle also. Without me testing it for who knows how long and putting who knows how much abrasive material through this, it's hard for me to say exactly how long this is going to last, obviously. Again, $25 for a nozzle you're not going to have to replace because really you're not going to wear this out in any reasonable amount of time. Seems like a good deal. But back to the wide shot. What's important here is now I'm going to put this nozzle on here. Like I said, they provided me one of these M2 nozzles. This is again a 0.4 millimeter nozzle. This is the RepRap design. Hopefully, maybe by the time publishing this video or soon after, they will also be releasing a MK8 version of this nozzle. But this is what I'm trying today. I'm going to put this, just replace the nozzle, nothing else on this printer. And just going to go back to the PLA. We've already done our sample prints here. I don't think there's any additional need to repeat any of these. Plus, I'm out of samples. So I'm going to put this nozzle on here. And you know what? I just changed my mind. You know what I'm going to do? I'm going to print some carbon fiber PLA through this nozzle. We're going to see how it does, see what the surface finish looks like. Then I'll have one more type of benchy and Deadpool here. I've got a whole spool of some old carbon fiber that's been sitting around. We're going to see how it does through this nozzle. I'll be right back with the results. Alright, so I was about to change out this nozzle, and I remember there's one more thing I wanted to show you, particularly in regards from switching to a non-all-metal hot end. So, if you remember, I've shown multiple times that if you're going to replace the nozzle when you've got a PTFE running all the way to it, you need to back it out. You have to then attach your nozzle a little bit, then you have to put the PTFE tube down it, yada, yada, yada. I've shown it before. But with an all-metal hot end, you don't have to go through those extra steps now. Let me demonstrate. So first of all, we will pull off our silicone sock. There we go. Pull that off. Now, we'll take the wrench that it came with and our socket, whichever type you're using. We just need to put that wrench on top the way we did when we installed it. Alright, now we can pull this off. Now this hot end is heated up to about 250 degrees Celsius, so we don't want to touch anything. Everything is really hot. But we want to do this while it's hot. Now we can just do this, and since we are taking this metal on metal, we no longer have to pull the whole thing apart. We can just change a nozzle and save ourselves a lot of time, because now we know this is metal on metal of our heat break, and there's no additional steps. Now I can cool this down, put the sock back on, and we are ready to print. So my test prints are complete. Let's take a look at the same prints that we were doing in the previous videos. So first of all, the stringing test. Now on this one, I wasn't able to dial it in any further. The same settings as before seemed to work as good on this nozzle as it did the other. But unfortunately, I did have some fuzz that printed on this one. It's not real strings, you know, there's nothing really connecting both, but there is a bit of fuzz on either side of the post. Now, moving on to the benchy, I don't see anything at all wrong with this benchy. My lines are really crisp. I have the same artifacts that I've seen on the other benchies that come from the slicer, but I have no overhang issues, and I have no stringing on this print at all. In fact, as you'll see here, I do still have the same stringing artifacts that I had on all of my other prints that I still believe are due to the slicer. Now, moving on to the Deadpool. Deadpool looks terrific, just as the other prints did with the other nozzle. In fact, the only thing I really noticed on this Deadpool is, again, there was some minor stringing on the top part of the katanas connecting to the head. It's really minor, And overall though, the surface finish looks really good and no other complaints about this. New nozzle seems to be doing great. So at this point, I want to take a step back for a minute because I want to talk about installing the RepRap nozzle on this MK8 hot end. So as you saw earlier in this video, the RepRap nozzle doesn't really fit this hot end correctly. It leaves a lot of threads between the nozzle tip and the heated element, and therefore the nozzle tip itself doesn't go all the way up to the heated element. That means that we're not getting the same quality of heating and heat transfer that we would get on a proper MK8 nozzle. And so that goes beyond what we saw with the stringing here, because in order to get it to print correctly, I ended up having to raise the nozzle temp about 10 to 15 degrees in order to get this level of quality. And I'm pretty sure it was because of the heat transfer and the cooling not being quite right with the incorrect type of nozzle. So I think it's fair at this point. Micro Swiss has already agreed that once the MK8 variation of this nozzle is available, they'll send it over to me and I'll do an update to this video where we'll do some more prints and I'll give you my final decision on this particular nozzle. But from here, let me give you my final thoughts on installing a Micro Swiss all-metal hot end. So to begin, I think it's important to note that I had preconceived notions going into this installation and testing. First of all, years ago when I first started with 3D printing, I had an ANET A8 that I installed a V6 clone on that was all metal. That was a terrible experience. It wouldn't stop clogging. When it did print, it would string. And so I ultimately gave up on an all metal hot end on that printer, thinking it was just too much trouble. So going into this, I didn't really know what to expect, but my expectations were low for the Micro Swiss all metal hot end. But as I showed you in the first two videos, it was a great experience. I had no problems with the Micro Swiss hot end. Now I'm happy to say that this hot end is going to be on this printer for the foreseeable future because it did such a good job at printing pretty much everything I threw at it, and I'm not really having to play with the retraction settings a lot. I'm not getting the stringing I was worried about. It just really does a good job. So a lot of that stuff I said before about the quality of the machining and the attention to engineering, that came from personal experience. I had bad experiences with a cheap product that really didn't meet expectations, and I tested this product, which is a little bit more expensive, but it really worked well because they take the time to do it right. So am I sold on the Micro Swiss all metal hot end? I think that's obvious. I'm a convert. I think this works great on these printers, and so I do recommend them. At this point, it's important to note that Micro Swiss has not sponsored these videos in any way. They only provided the hardware for my testing. The review itself was completely constructed by me, and the results were my own. Now, I've heard from a few of you that you're still having some issues with your Micro Swiss hot end. If that's the case, I have a couple of pieces of advice for you. First of all, if you haven't tried my 4mm, 40mm per second settings, please give those a shot. They worked great for me, and they worked fine across multiple filaments. 2, check your cooling fan on your heatsink. If that fan doesn't appear to be blowing at full speed, or you feel like it's just underperforming for some reason, I recommend changing that fan. If you're getting clogs, it could be that that heatsink is not cooling as efficiently as it should, and that you're getting some heat creep. So check that out. Third, I found a great channel called Dr. Vax. Video link up here. He did a couple of videos on the Micro Swiss hot end, and one of the videos was, there are people having problems with the Micro Swiss hot end. Why are they having problems? I recommend checking out his video. He goes through a lot of the issues that he found on various boards and how he thinks you could fix those issues. So let me go and forward you to him rather than reproducing his content. Well, that's it for this video series. I hope you've enjoyed it and I hope you've learned something. As I told you, this is much longer than I planned for it to be, but I hope I packed in more information than you were expecting and that you got more out of it than you were expecting. Lastly, I would like to thank 3 Patreon supporters that have come on recently. Joe, Carmelo, and Daniel. I don't believe I've sent a shout out to you, but thanks for joining my Patreon. Thanks for supporting this channel. I have links to all of the products that I've discussed here in this video or in this series. You'll find them in the description. Click on those links. Support Micro Swiss if you think this is something you want on your printers. Support this channel by following my affiliate links. Again, thanks for watching. Like, subscribe, share, all that good stuff. I'm Chris, and this has been Kersey Fabrications. Thanks for watching.